Hi everyone, today we will discuss the topic of general organic chemistry, that is bond energy, bond enthalpy, or it is also called as potential energy of a bond, right? So what is meant by bond energy? Bond energy is nothing but, or bond enthalpy is nothing but the amount of energy required to break 1 mole of specific covalent bond in the gaseous phase. It is defined as the amount of energy required to break 1 mole of specific covalent bond, or we can also say that specific chemical bond. Directly we can say it is the amount of energy required to break 1 mole of specific chemical bond in gaseous phase. Any chemical bond means it may be ionic bond, it may be covalent, it may be van der Waals forces of attraction. It is nothing but the bond energy is nothing but the amount of energy required to break 1 mole of specific chemical bond. Either it may be a CH bond, or it may be Ci, or it may be the Na plus and Cl minus, the ionization energy, which is also called as bond energy. In ionic compound, we can call it as ionization energy. In organic chemistry, we can call it as bond energy. Right? The amount of energy required to break 1 mole of specific covalent bond in gaseous phase. Right? It will be measured in terms of kilojoules per mole. It is measured in terms of kilojoules per mole. Let us consider the example with carbon and hydrogen and carbon and iodine bond. We can directly tell the bond between hydrogen and carbon is highly stable compared to carbon and iodine. The bond between carbon and hydrogen is stable due to the electronegativity difference between carbon and hydrogen is less. Carbon is more, no doubt, carbon is more electronegative than hydrogen, but the electronegativity difference is less. We have discussed this concept in first video, right? The electronegativity difference is the iodine is much more than carbon, and the size of iodine is much higher than the size of carbon, right? This is due to steric hindrance. The bond between carbon and iodine is weak and carbon and iodine is high. We can explain it through the energy profile diagram. Let us consider that too. Let us discuss the energy profile diagram of carbon and hydrogen. The bond between carbon and hydrogen overlaps by the 2p orbital of carbon and 1s orbital of hydrogen. Carbon 2p orbital and hydrogen's 1s orbital. These two overlap will give sigma CH bond and sigma star CH bond, right? We know that effective overlapping, the overlapping of 2p orbital of carbon with 1s orbital of hydrogen is great. Excellent overlapping is formed between 2p orbital of carbon and 1s orbital of hydrogen. This means effective overlapping means we know that large splitting will be occurred in case of bond formation, right? Larger splitting will be occurred in case of bond formation. Hence, the energy difference between sigma CH to sigma star CH is more. The energy difference between sigma CH and sigma star is more. Large energy gap. Right? The large energy gap means larger splitting means what? The sigma of CH is pushed much lower energy and making it very stable, right? Much lower energy means sigma of CH is highly stable. Lower energy, high stability, highly stable. The splitting will push the sigma CH to much lower energy That means the sigma CH it is having high stability, and the bond between carbon and hydrogen is very difficult to break. The bond between carbon and hydrogen is very difficult to break. Let us consider the energy profile diagram of carbon and iodine. We know that in the overlapping will be occurred between the 2p orbital of carbon and 5p orbital of iodine. We know this the carbon 2p orbital is overlapping with iodine 5p orbital, and the iodine 5p orbital is very large and diffuse. It overlaps poorly with a smaller carbon, that is 2p orbital of carbon. It will overlap poorly with the 2p orbital of carbon. Hence the splitting will be less. The splitting will be less. Less splitting means it is also, no doubt, it is also form sigma Ci and sigma star Ci, but the energy gap between sigma Ci to sigma star Ci is less energy gap. Less energy gap will be there between sigma Ci to sigma star Ci. This means the less splitting will push the sigma Ci to higher energy. Higher energy means it is in higher energy. That means it is less stable. Less stable. Less stable, which is having high energy. And the bond dissociation energy in carbon and hydrogen is, the dissociation energy of this CH bond is 413 kilojoules per mole. 413 kilojoules per mole. But in carbon and iodine, it is, the bond dissociation energy of carbon and iodine is 240 kilojoules per mole. This is due to the less stability of carbon and iodine and the more stability of carbon and hydrogen. Hence, the bond between carbon and iodine is weak. The bond between carbon and iodine is weak compared to carbon and hydrogen. It is strong bond. Let us make a quick summary of CH and Ci bond. CH and Ci. The bond in orbitals involved are carbon 2p orbital and hydrogen 1s orbital. These two orbitals were combined to form CH bond. Here carbon 2p orbital overlaps with iodine 5p orbital, and orbital overlap is excellent. These two orbital overlaps excellent manner. Excellent overlapping is there between carbon 2p orbital and hydrogen 1s orbital, and here poor overlapping is there. Hence, the energy splitting is large. Energy splitting between what? Sigma and sigma star is large. Here, energy splitting is small. And the sigma bond energy is in lower energy state. The sigma bond is in lower energy state. Lower energy state. And here, sigma bond is in higher energy state. Sigma is in higher energy state compared to CH. Higher energy. And bond strength is, the strength of the CH bond is strong. It is high. Bond strength is strong, and bond strength is weak. Right? Hence, the bond between Ci is weak compared to the bond between CH. On the molecular orbital diagram, also we can say which bond is stronger bond and which bond is weak. With all these, we get to know that bond energy is less means bond energy less. That means it will form more stable bond. More stable bond. Right? Here the carbon hydrogen bond energy is less. The carbon hydrogen bond energy is less. That means it is highly stable. And another one is stable bond means, more the stability means it will requires more energy to break. Right? More the stability, more the stability, more the stability, more energy is required, more energy is required to break the bond, to break the bond, right? Stability increases. This means the stability increases, the stability increases, bond dissociation energy will, bond dissociation energy will increases. Stability increases means what? Bond dissociation energy. All these relations, with all these relations, we can directly tell that S character, we can later discuss with this, S character is directly proportional to bond strength, which is inversely proportional to bond energy, and which is again directly proportional to bond dissociation energy. As the bond strength is more, the bond dissociation energy is more, hence it is directly proportional, and the bond dissociation energy is inversely proportional to bond length. Let us discuss. We know that triple bond, double bond, and single bond. Yes, here S character is high in triple bond, right? S character is high in triple bond, that is sp hybridized, and this is sp2 hybridized, and sigma bond means it is sp3 hybridized, right? S character is more in sp, that is triple bond, and compared to double bond and single bond, sigma bond. And we know that the bond strength, right? Bond strength is directly proportional to the S character. Therefore, triple bond is highly stronger than double bond and sigma bond, right? And bond length, bond length in sigma bond is more compared to double bond and triple bond, right? Bond length is, we have discussed S character, right? S character increases, the bond strength will increases, and bond length will decreases, right? The bond energy, the energy required to break the bond is decreases, right? Okay, right, in CH and CI, the energy is high in CH and CI. In CH and CI, the energy is high. Energy is high in case, energy is high in case CI compared to CH, right? And stable bond means bond strength is more in case of CH compared to CI. Bond strength is more strength. I am speaking about this bond energy. Bond energy is, I am speaking about the bond energy between Ci and Ch, right? The bond energy is high. The energy in energy profile diagram, the Ci bond is having higher energy compared to Ch. That I am speaking here, right? Let us discuss. Let us consider this as potential energy. Potential energy. That bond strength increases. The strength in Ch is high compared to Ci. Hence, the bond strength increases. Bond energy decreases, and bond dissociation energy is increases. Here, the bond dissociation energy is high in case of Ch due to strong bond comparatively with Ci, right? Example, in A, B, and C, which one be the homo? Which one will be the homo? Give the order of donor-ability and give the order of acceptor-ability. In ABC, give the order of donor-ability, and in ABC, give the order of donor-ability. Let us discuss example. In ABC, give the order of donor-ability. We know that, make a point, electronegative group decreases the energy of the system, and electropositive group electropositive group will increases the energy of system. Right? In the given example, there is a discussion about carbon, nitrogen, and oxygen. Here, the electronegativity difference is there. Oxygen is more electronegative than carbon. Sorry, oxygen is more electronegative than nitrogen and carbon. Hence, let us discuss the energy profile diagram of these three. In the case of energy profile diagram of carbon, nitrogen, oxygen, let us consider a band gap. Let us consider a band gap energy is there. Band gap is there. Okay, carbon, 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 nitrogen, and carbon, oxygen. Oxygen is more electronegative than nitrogen than carbon. Oxygen is more electronegative compared to nitrogen, compared to carbon. Hence, it will lowers the energy. In all the cases, pi bond will be there. Here also pi bond. Here also pi bond. Hence, there is a pi and pi star energy levels. Pi, this is pi, this is pi star. Due to electronegative atom, the energy was decreased. The energy was decreased. Here in carbon and nitrogen is less electronegative than oxygen. Hence, it will be there in the slight higher energy in energy profile diagram. So here this is pi star, and carbon electronegativity difference is less compared to nitrogen and oxygen. It will exhibit higher energy in the energy profile diagram. That means pi, this is pi, and this is pi star, right? That means the pi energy of carbon pi star is more than nitrogen, sorry, Cc pi star and Cn pi star, and the energy of C double bond O pi star, right? The energy of carbon pi star is more, right? Here the energy is more. The energy is more. Here due to oxygen electronegative atom, the energy is less. Energy is less. We know that in question they were asked about give the donor ability, right? Give the donor ability of the ABC, right? We know that donor ability means donor ability they are speaking about homo and lumo. Homo means that is having highest energy among these three. Which was having highest energy means carbon pi star is having highest energy. Hence that will donate electrons more comparative to carbon nitrogen bond and carbon oxygen bond. Hence the donor ability in A is greater than B and greater than C. Like this we have to solve the questions.